Thank you. Thank you very much. It's a pleasure to be here, and I want to thank the organizers for inviting me to talk and to participate to this program. So the lecture will be about the localization of gravity effect or shielding of gravity. And typically I'm going to talk about localization in cones for asymptotically flat solutions to the constraints. So everything here will be Riemannian, will be a space-like slice. And I want to show you that there are a lot of solutions to the constraints, as we know. But what I want to do here is to tell you things about the asymptotics and how you can include harmonic terms in these conical localization. So somehow questions that were left after work by Piotr and Delay and Carlotto and Schoen in this direction was to go to harmonic, to discuss harmonic terms in the localization setup, and in some sense to say where is the mass, where is the contribution from the mass, because we are going to talk about solutions that are highly non-spherically symmetric at infinity, right? So some angular direction could be completely flat, some other angular direction could be exactly Schwarzschild, and I'm going to talk about gluing between these two things, right? So when you measure the mass at infinity, you may wonder how you compute the mass in some sense. And this is what I'm going to talk about. The work is joint with Bruno LeFloch, so he's at the same university, but in a different department, in this laboratory of high energy physics. And he's also my son, and we have been working for the past few years together. The equations are, as most of you know, an equation for the Hamiltonian. I mean, you have the Hamiltonian constraint, the momentum constraint. And so the announce, when you want to describe your initial data set, the data that you are looking for are the induced metric on this initial slice plus the extrinsic curvature. And these two quantities satisfy the system of a scalar equation, which is a kind of prescribed scalar curvature problem, coupled with a divergence equation so you have basically one scalar equation and one vector valued equation for the momentum. My notation will be as follows. So I'm going to use, I'm not sure I use this notation very much in the following, but probably at some point, curl H stands for this operator, curl M for the divergence operator, or curl G when you put the two together. And instead of working with K, I'm going to work with a sort of translation defined by that. So my announce will be G and H, and the sharp symbol is a symbol that raise or lower indices. So something quite important. Okay, there are two methods that are known in the literature. One is called the conformal method, where you give me a solution and then you add a conformal factor and you solve for this conformal factor. And this technique, or even more involved after that, but originally it was stated in this form by Lichnerovich in the 60s, and then many people worked on this technique. But now there is also another technique more recently introduced by Corvino and many people who followed in this direction, which consists of making a metric, a deformation of the metric. So you have a certain solution, it could be a solution, or maybe it's not a solution, but you perturb it in some way. The perturbation is typically picked in the image of the linearizer joint of the Einstein operator. And by looking for gamma, you actually produce solutions. So this is called variational because there is a variational principle behind in order to pose the problem and state some well-posedness existence theory. As we know, there have been major achievements by these two techniques, and this is of interest in general relativity, but also in Riemannian geometry, existence of initial data sets. We have to make sure that they are interesting from a physical perspective. But there are many classes of such solutions, many recent results or older results. And typically, what you can do here is you can take two solutions and glue them together, right, along some gluing domain. And you solve in a gluing domain. Outside, you assume that you have exact solutions. So there is just nothing to do. You solve in a gluing domain, and hopefully you produce a new solution by gluing in this way. So there are many results depending on the topologies that you want to study. And for me, everything here will be asymptotically Euclidean. And I'm going to start from the work of Carlotto and Schoen a few, maybe now 10 years ago. So what Carlotto, Schoen did, and also Cruciel and Delay, was to exhibit phenomena of anti-gravity or shielding at infinity, which basically allows you to construct solutions that were very much unexpected at that time. So you have a solution that is asymptotically flat, and you can go in many different angular directions, and eventually, maybe after some compact, outside some compact region, you can assume, you can construct solutions that are completely flat, completely Euclidean in such directions. But of course, this is not possible in every direction. You cannot construct compactly supported solutions because of the positive mass theorems that prevent you from doing that. But yet you can do that provided you still allow some cone at infinity, which can have a very tiny angle, possibly. So this was proven by Carlotto and Schoen in that paper in 2014, where what they implemented was a gluing of the Euclidean metric and the Schwarzschild solution. And the result was producing a solution in the gluing domain. So they were really solving between two cones at infinity. And the solution they constructed had a certain decay, but the decay was not, maybe not the one you would have expected, which is they were able to, with their method, they were able to derive a subharmonic control where the exponent p is strictly less than p minus n minus 2, which is the harmonic rate. Now, more recently, after that, I work with Tika Nguyen, and we propose a technique, I'm going to talk briefly about it later, where we could actually achieve the rate n minus 2 and higher inside the gluing, but this was with a modification of what the localization problem meant, and we defined something that we call asymptotic localization problem. I'm going to say more about it. And so it's only in recent, last year, that this optimal localization for the constraint was achieved with Bruno. And so our result is a result where in the gluing region, we control the solution at a superharmonic rate of decay. And in particular, we can tell you what happens with the term at the level of the mass, you know, the 1/r term. We get the shape of the transition in the gluing region. So this is basically the main point of this lecture that I'm going to tell you more about. So I have a picture here that represents a manifold with two ends. So one end we put Schwarzschild, or say over there, and the other end is where the gluing is taking place. And we do here 3 pictures that correspond to exact subharmonic localization, or asymptotic superharmonic, or exact superharmonic localization, which means the following in the picture. Outside the orange part is just completely flat, is Euclidean. The purple region is exactly Schwarzschild. And the gluing region is what you see in the red over here. And so in the first picture, everything is supposed to decay, you know, with a certain rate, but the gray red part here is not decaying as fast as Schwarzschild. In the last picture, if you wish, you see a decay in the red region, which is the same decay. I mean, this is what the picture is trying to show you, to illustrate. You see that the decay is of the same order, 1 over r, as in the Schwarzschild region, right? So there is no artificial bump somehow in the gluing region where you would lose some control of the decay of your solution. So this is the last picture. And the picture in the middle, you see that there are some wiggles in addition. So the decay over here is really everything that happened at the 1 over r rate of decay. But since I told you that our localization was not exact, it's asymptotic in some sense, we had in this proof, with this technique, some additional waves in some sense, you know, that had a very high decay, faster than 1 over r, but in a way they spoil the geometry outside the gluing region. But it was still, I think, an interesting intermediate result by the fact that it was essentially solving, from a physical perspective, maybe the conjecture that was put forward by Alessandro Carlotto and Rick Schoen. In our construction, we allow nested conical asymptotic end, and I should point out that Piotr Kruciel had a lot of various construction of ends with a very fancy pictures. So this one is not that fancy compared to the ones that Piotr had, but we do that. We do this kind of nested asymptotic end. And again, the new feature in the technique, and the paper is quite technical to reach that, is to be very careful about the behavior of the 1 over r terms in the construction. Okay, so this is another illustration of the same story. Maybe you would understand also this picture, but just a different illustration of the same phenomena. And so what I'm going to do now is to state the first 2 results briefly, and then move forward to the main result where everything is controlled in some optimal way. So the subharmonic localization by Carlotto and Schoen localize that. So you give a name to the various cones and regions. So you have maybe a tiny cone, you have the complement of a slightly bigger cone. And so this defines some intermediate region between the 2 cones, which I call T for transition region. And what is done here is to solve within these 2 cones, right? This is a region where you want to solve your elliptic, your nonlinear elliptic PDE, which is behind. So here you achieve Schwarzschild in a tiny cone. You achieve that the metric is exactly Euclidean outside a slightly bigger cone, and in between you get a decay for the gluing, which is with this exponent p strictly less than n minus 2. So as already mentioned, Carlotto and Schoen, they conjecture that geometrically, you know, they would like the gluing to be done at a level where the solution remains 1 over r in the transition. Okay, but so maybe they thought at that time that it would be a small modification of their proof, but it turned out to really be quite heavy to get the proper setup to achieve that. Now the second result is a result where the localization is only done in an asymptotic sense. So what I mean now is that I'm happy when I do this kind of gluing, but I should probably already mention that we are not, in our proof to achieve what I'm going to state now, we are not solving in a domain, in a gluing domain with boundaries. So the philosophy for the second result was actually quite different. And you know, because the technique was quite different, the way the result was a result where if we attempt to glue Schwarzschild and Euclidean, as I explained, the result is the following. The result is that in the small cone, the metric is Schwarzschild plus something with a very high decay. So very high decay means this P star strictly bigger than n-2, right? And same similar statement in the Euclidean region, same with a P star strictly bigger than n-2. And in between, we were able to get the 1 over r n-2 decay as well. So again, we were solving, for this method here, we were solving the Einstein equation over the whole manifold, or at least outside some large compact region, but we did not distinguish between angular regions. And the philosophy, or not in the first stage of the proof, and the philosophy here was to prescribe some asymptotic behavior through the notion of C data set. I'm defining it in a minute. And so having a kind of asymptotic behavior prescribed, we were able to construct a natural solution. And then in a second stage, we were able to modify the C data set somehow any way we want by introducing certain parameters. And by doing that, by choosing the C data set to be highly non-spherically symmetric and trying to push the solution to be Euclidean in some angular directions, to be Schwarzschild in some other angular directions, we were able to fix these parameters and eventually achieve the result that is stated here. Okay, so the philosophy was prescribe some kind of asymptotics at infinity, and you can play with that. You can do some variation of the seed data, and given the seed data set, I produce a solution. But the control of the solution, I mean, it's a bit tricky, and you have to pay attention to that. Yeah. Yeah, there are parameters to. Yeah. No. We can prescribe the mass, right? I'm just telling you that what is not controlled are higher order terms, right? But at the level of the mass, everything is prescribed. Okay, and so this is maybe a statement of that result. So I'm still describing the case of asymptotic localization, and this was based on this idea of so C2 solution parametrization. A C data set is so something you prescribe at infinity. To describe it, you need to specify. I mean, I'm not giving you the parametrization of that, right? I'm just telling you that by definition, a C data set is something that is asymptotically flat with a certain exponent, PG. G stands for geometry, the geometric decay that I prescribe. And when you plug, so you do this ansatz at infinity in such a way that if you plug it into your operators, the Hamiltonian of the momentum, you get a certain decay, but of course, better decay if you have adjusted your ansatz properly, right? So there is a second exponent, so A stands for approximation, and this exponent here has to be in a certain range, etc. So assuming these ranges that you prescribe at infinity, then we are able to construct an actual solution of the constraints, vacuum case. And now we distinguish between various, accuracy of your ansatz, right? Your ansatz may be possibly a bad ansatz in the sense that you only make it to be subharmonic. So in this case, you have an agreement between your ansatz and your solution, which is what you may have expected. Now, you can also define the ansatz by paying attention to the mass, to the 1 over r terms, in dimension 3, right? So in this case, you construct a solution which actually contains some extra spherically symmetric terms, right? So 1 over r terms that comes in addition to the prescription you have done, but to reconnect with what Piotr was asking, there will be a parameter here that is can be adjusted by implicit function theorem. So basically, what I'm stating here is like the fundamental result, where I'm explaining you that there are some additional terms that come in this construction from seed data to solution. There is an effect of a 1 over R term with a certain mass term. And then in the second stage, you play with this mass term any way you wish. Okay, and the third regime would be superharmonic decay. So you construct your ansatz very carefully somehow, at a higher level. And then this is the result that you get. So the question is, how big is this M, right? Because G1 could be Schwarzschild, so there is already a mass term in it. So there is, in some sense, a correction to the Schwarzschild effect that you put in your ansatz, say, Schwarzschild mass contribution. And this is something that we call a mass modulator. And this mass modulator is directly connected to, say, to the error of approximation of your ansatz, right? So I'm computing on, or evaluated the operator on the ansatz, computing the total integral, and this gives me an idea of what kind of correction I would need to do, right? So this is like the beginning of what you have to observe if you want to do a fixed point argument and adjust the coefficients the way you want, okay? But behind that, there is a map that goes from seed data to a solution. And this is what this theorem is talking about, right? How this map, seed data to solution, what it is doing. And then you play with the seed data, you adjust the seed data, and if you don't like the result, which is this one, then you adjust the seed data and you arrange this mass corrector to be anything you want. Okay, now in the optimal series that I got with Bruno, we have an exact localization. We can cover slow, fast decay with a whole possible range of exponents. And importantly, we control the solution with sharp estimates that are superharmonic. The domain could be also a little bit fancy, these conical domains. So how we formulate that? So we have a Riemannian manifold together with, so everything will be again asymptotically flat. There is a gluing domain, which we call omega. We have in our manifold, we pick up some point and we define a certain radius function to compute the distances from a fixed point in a manifold. So there is this function R. And in addition, in the gluing region, we want to define a certain function of localization, lambda, which is essentially the distance to the boundary, right? And maybe I have a picture, maybe in some other page. So we have the distance to the boundary, but it has to be rescaled in terms of the distance, right? Everything is asymptotically flat, so there is a distance to the boundary, and there is a distance toward infinity that we also should take into account. So this quantity lambda is a way to measure the distance to the boundary in our domain. Now, the formulation of the constraint will be based on a weight that localize your equation to the gluing region. So there will be a lambda, this function lambda here, to some large power, capital P. So we have really two letters here. One is a capital P, which is a localization exponent. It tells you about the regularity when you approach the boundary. So capital P is just a large number. That's not very important. But there is also a small p, so it's not extremely visible on the screen, but this is a small p. And this small p is very important because it has to do with the decay of the solution, okay? So there will be several exponents called p or pg, pa, p star, which are all important and they play different roles, which I'm trying to explain. So the first exponent here, p, is strictly less than the harmonic exponent and is called the projection exponent. It comes also in the weight. So the weight also contains a weight in terms of the distance, right? So this omega p is going to come into the variational formulation in a minute. So you have this picture again, and yeah, so this is a plot of lambda. So it's linear when you approach the boundary. This will be a picture when you do a cross-section, across the gluing region. We have some numerics. Actually, this is a picture that I got from our numerical section. And so now what we do. So far I didn't say much about the gluing region. So we assume that the gluing region is has a conical shape, if you like, but conical could mean still very different things. And the important thing is to realize that because of the scalings that I made of this localization function over the distance, you can really think of this lambda as being defined on the sphere at infinity. So this is what we are going to do here. We are looking at the asymptotics. Part of the analysis will be on the sphere at infinity. And on the sphere at infinity, we have a certain domain that is the intersection of the cone with the sphere. And lambda is a function that characterizes the gluing region at infinity. So lambda is defined on the sphere, and it is a certain function that goes from 0, say, over here to some irrelevant bounded value in the middle, say, of the gluing domain. Now, we have a way to define a projection, and this is done by having a kind of reference, which we call localization data set. So this is a not very important reference that says that our solution will be asymptotically flat with a certain rate. Okay, so now at this stage, we have this projection exponent. So I didn't say exactly how it comes in the picture, but it defines the solution map and the variational formulation of the Einstein constraints. There is a geometry exponent that tells you what kind of decay you allow at infinity, and this PG will be arbitrarily small, possibly arbitrarily small, just positive. And then will now come two more exponents, and the first one is the accuracy of your ansatz. And the accuracy over here should be greater than the projection exponent over here, the geometry exponent here, and is going to arise in the next slide. So I still didn't tell you, how I do the construction. So this comes now. How we do the construction. So we define something we call a localized C2 solution projection operator. So we think of a collection of C data, and we want to think of the construction as a projection operator that takes an approximate solution and generates an exact solution. And so this is done by introducing an operator. We call it solution. It depends on the dimension, it depends on the projection exponent, it depends on the choice of the localization function, and it takes a C data, localized C data set, which means that. So it means that our C data is our reference metric at infinity plus a certain certain decay that is localized. So G0 will stay outside the gluing region. We are not solving any PD, right? So outside the gluing region, we already have prescribed our solution, and this is this G0, right? And we solve inside the gluing region, and we have this this weight that takes into account the decay in space, and it also takes into account the localization as we approach the boundary. This lambda is going to 0. So our C data or our solution, when you approach the boundary of the gluing region, should reconnect with what you have outside in order to achieve enough regularity in the construction. Okay. So the second condition I mentioned before is a condition that this seed data should be an approximate solution of the Hamiltonian and similarly the momentum. Okay, so now what you do is that you make a deformation of the seed data. The deformation means that you had a certain gamma to the metric or a certain eta to the component H, and this is done by linearizing the equation, looking at the dual of the linearized Hamiltonian or the dual of the momentum Hamiltonian, putting a proper weight like I told you before, and this is a range where you look for the deformation, right? So the deformation is assumed to belong to that. And the reason for that is that behind it, there is a variational formulation that allows you to get nice estimates on your solution. Of course, the deformation should be done in such a way that the equations are satisfied, right? So the equations I've written in the second box here, they involve the nonlinear operator, G, the nonlinear Einstein constraint. They involve the dual linearized around some fixed G0, H0, something that we have fixed from the beginning. And the unknowns here are the U and Z. So U is a scalar field and Z is a vector field. And by varying U and Z, you can vary the deformation, and you do that by achieving the exact solution by solving this equation. So it turns out that this system is nonlinear elliptic and can be solved in suitable weighted spaces, which are mixed of Sobolev and Hölder spaces. Okay, we like to see this kind of construction that go back to Corvino and Carlo Torschen and Piotr Kruchiel and Erwan Delay. We want to view this construction as a projection, right? So there is an operator behind, and we can write like error estimates or continuity estimates, this kind of things, and to think of it as a way to parameterize. I mean, this is really when you have these constraints, to have proper classes parameterized by some parameters. I mean, this is essentially an open problem. If you would like to look at all solutions, of course, this is far from being realistic. But here we have a parameterization of a certain class of solutions, and this parameterization can be seen as a projection operator in asymptotically flat solution with certain decay at infinite. Okay, I'm writing here the equations, and just to summarize again, that we have a formulation that built on many earlier works and allow us to see the construction as a projection, and make sure that we distinguish between various decay exponents that have really different roles. So this was really important in our analysis to understand that the projection exponent that comes everywhere in this operator as a singular weight was in a certain range, subharmonic, and then that the geometry decay could be arbitrarily small, and we also had a certain range on the approximation exponent here. So to have a good picture, a good understanding of the range of these exponents was quite important before moving to the next stage of discussing harmonic terms, okay, which I'm going now to do. Okay, so the optimal localization is done by introducing what we call a sharp decay exponent. So it's an exponent that is bigger than P and less than this P approximation. So in some sense, you cannot hope to get an information beyond the accuracy of your seed data. So this is the range that is in principle expected. But more precisely, the most interesting range is a range where you can choose in the estimates I'm going to write now, you can have this sharp exponent to be strictly bigger than the harmonic term. And in addition, as you will see, the analysis is based on various Poincaré, Korn, Hardy inequalities involving this function lambda as a weight. And so there is a certain limit to the range you can cover, and there is a limit here beyond, which is not n-3, as maybe you would like to think in the case without localization. Okay. So if you think of some of the results I stated before, you can imagine that the kernel of some asymptotic kernel will arise in a picture. So I'm going to explain this in a minute. So there are some things that we are going to call the asymptotic Einstein operators. We'll take the constraints, linearize at infinity, and then make a decomposition. So certain operators, a double slash that I am introducing here, will be relevant, will have kernels, and these kernels, one will be for the Hamiltonian of dimension 1, for dimension n for the momentum, and they precisely produce this 1 over r terms at infinity. So that's part of, maybe the main part of the story is to understand these kernels and their dimension, etc., at infinity. But having these kernels, what we prove is that given the seed data, so you look at the map, there is already a solution, because the previous C2 solution map is producing a solution for any seed data. And now what I'm doing is that I'm analyzing, trying to do some analysis of that solution. So I take the solution, I compare with the seed data, and what we observe is that there are some harmonic contributions, and that's what we want to do now, how to describe these harmonic contributions at infinity. And what I'm telling you is that there is an effect of a kernel at infinity, which you need to define. I didn't tell you exactly what these are. And having these kernels, what you do is that you add to the seed data 1 over r contributions that are elements of this kernel, which are contracted with some vectors that we call space-time energy momentum modulator, right? So this will be just constants, if you like, and the kernel elements are non-trivial, which we are able to compute numerically in some cases. They are non-trivial element on the sphere at infinity. So they really give you the result of how the mass is distributed if you glue Schwarzschild with Minkowski, what is really going on at the 1 over r level. So the new method is based on deriving sharp integral and pointwise estimate for the linearized Einstein operators, which are fourth order in our formulations, this variational formulation. They are actually fourth order and second order respectively. And so to do that, to get the stabilities that we want, we had to uncover certain stability conditions. That depends on the choice of your localization domain and your localization function. So there is some weighted measure on the sphere at infinity in a domain, we call it big lambda, the trace of the gluing domain on the sphere at infinity. There's a weighted measure, and we discover harmonic radial shell stability conditions that are certain coercivity condition for our operators, more precisely for various contributions, as I'm trying to show you. Okay, so the result stated now more precisely is like that. You give me a conical localization data set with these exponents. So this is a full range that you might expect to cover. The projection is subharmonic. The geometric decay is any decay. And the approximation decay has to be, for this statement, should be taken to be bigger than the harmonic level. The localization function at each asymptotic end should satisfy certain weighted Poincaré Korn inequalities and RD inequality. And if you pick up a localized C data set defined by, characterized by these conditions, then there exists a solution to the Einstein constraints defined by this nonlinear variational projection. And now we describe the asymptotic of that solution by saying that it coincides with a C data plus something with a very high decay, bigger than n-2, right? This is what this line is telling you, except that the C data here has to be modulated in a way where the modulated C data set is equal to the given C data set up to contribution from the kernel of the Einstein harmonic operators, which I'm going to write. Okay, so what we have as an assumption in this theorem are coercivity inequalities, Poincaré Korn with certain weight, which cannot be true in general, right? If you take a very crazy localization function, these coercivity condition maybe won't be satisfied. But this is not the point. The point is that you can, within any domain, you can pick up localization function achieving these inequalities. And this is what we do. So behind that, there is a question of computing the optimal constants in these a little bit complicated Poincaré Korn inequalities. And we do that, for instance, in arbitrarily narrow gluing domains. So this is something that we really wanted to understand. In the previous picture, maybe I didn't really show example in that spirit, but you really would like to localize everything in a very narrow domains, and we prove that. We prove that these coercivity conditions hold in such domains. So I guess I have another 10 minutes or something, 15 minutes, okay. So the operators are written here. So I mentioned before that they were elliptic, and you can solve these equations. There are some weights, but these are elliptic equations that are quite well behaved. And so if you want to understand the asymptotics at infinity, you need to obviously to look at your linearized operators at infinity. So evaluated on a reference metric, which is the Euclidean metric, and this is what I'm writing here. Okay, so these are the main operators you need to study. So one is like a kind of bi-Laplacian, and the other one is a vector Laplace operator, but it's a little bit yeah, not quite that. And what's important here is that there is this weight, which is again something which is singular at a boundary, and which also involves a decay in space. Okay, so you look at these operators, and you want to say something about the asymptotics, and the way we do that is that we take the operator and we make a decomposition where maybe the most interesting part is the last part here, which you obtain by plugging harmonic decaying functions into your operator. You know, it would be like you try to find one over R exact solution in this problem. But these exact solutions do not exist, but yet you can find a main behavior by, in this operator, plugging solutions that are nu. So nu will be a function defined on the sphere at infinity over this power of R. So you may find it surprising that this is not just nu over R n-2, but this variable u is actually the dual variable that came in the variational formulation before, right? So it happens that in terms of the dual variable, this is the analog of the harmonic exponent for the dual variable. Okay, so this is the operator that we study. Okay, so we study this operator that comes at infinity, by saying, I'm interested in looking at the sphere at infinity. We expect 1 over r terms for the metric. We work in this dual variable, which is called u. We look for harmonic decaying functions. And what is a PDE relative to this variable nu here, okay? And it's given by that. So everything here, the slash, means that you are looking at the sphere at infinity, and you have a sort of bi-Laplace operator on the sphere at infinity, which involve coefficient A and P, which is given by that. So again, depends on dimension, it depends on projection exponent. And so this is a question. If you can control coercivity and stability associated with this operator, or the kernel of this operator, then you understand the 1 over r terms in your solution. Okay, so that's basically what we have done. Let's say something similar for the momentum, and we discover, we found conditions of stability that tells you that the kernel of this operator has dimension 1, as you expect, and for the momentum, the kernel has dimension n. And we do compute the Poincare constant in narrow gluing domains. Okay, so I think this is maybe this is a way to describe our results. There is more to it because when you do that, you're only looking at one part of this operator, right? But there are other parts. There is a part that involve only radial derivatives that will be important if you want to look at the average of the solution on the spheres, etc. So there is a lot of structure behind that comes from decomposing the linearized operator at infinity. Okay, I probably can, maybe let me say a little bit more about that. So we call the element of the kernel properly normalized, and I am going to tell you why we need a certain normalization. We call it silhouette function. So it's really, again, it shows you the shape of the solution at infinity. So it replaces the 1 over r terms is somehow replaced by this nu over r contribution at infinity, but localized in a certain domain. Okay. So this is maybe a little bit heavy expressions, but basically what you want to know what is the effect of this element of the kernel on the metric, right? So the metric is going to capture 1 over r terms, but in this variational formulation, we are saying that the G and H are in a certain image of the linearized operator. So in the end of the day, it goes like that. You look at this kernel. I show you the operator explicitly in the previous screen. Take the kernel, give a name silhouette to the solution, one-dimensional solution, the kernel. So give a name to it, normalize it in a proper way. So the normalization is not trivial, and it has to be done in this way if you want to get a nice formula for the mass in the end of the day. So you do that, and then you plug it here as a correction to the dual variable. So this is a scalar quantity. The iota stands for number for the asymptotic n. So this iota is completely forget it. And this is the element of the kernel. It's defined on the sphere at infinity. So for us, x over r is an element on the sphere at infinity. You divide by the proper power of r, and then you plug this in this formula, and you get the correction to the metric. And if you look carefully, it really means that you have an 1 over r correction to the metric. So this correction is 1 over r times certain second order derivative of this element of this kernel. Okay, so explicit formula that we can compute. So we have done that explicitly in the axisymmetric case. We have computed these things. And so from the element of the kernel, you do a linear combination. In a Hamiltonian, it would be just a scalar quantity or for the momentum, you have a vector here, right? So these formula are describing exactly what is 1/r contribution on the sphere at infinity, localized in our gluing domains. Okay. So this is probably enough for the story. Let me skip. There is a formal statement here, which essentially I can skip, except to maybe tell you that we have a formula, like I show you in the asymptotically localized system. So there are some contribution to these kernels, which are given this name, M infinity, and they're actually very close to quantities you can compute explicitly by integrating the Hamiltonian on the seed data, right? This gives me an idea of what should be the mass correction. And indeed, this is the correct order of magnitude. And this is the beginning of a fixed point argument that you can do to adjust this number any way you want. Okay, you would like a certain formula for the mass, which we have here, so we can say, okay, there's maybe another point here, is that the solutions are decaying extremely slowly, so they don't have an ADM mass, okay? But somehow I don't care, because only the difference between the seed data and the actual solution is important for me. I mean, this comes in this discussion. Only the difference. I just want to say something about the 1/r terms, these corrections. And so I can do that by calling relative energy, relative momentum vector, the mass and momentum that you produce by just computing the difference, which has enough decay to plug it into these classical definitions. And thanks to our normalization, we can really understand as a notion of mass and energy momentum these correctors. Okay, let me try to finish. I will skip that, and maybe I show you just a little bit about the numerics. Maybe just 2 minutes. So we computed what we have called silhouette functions. We computed that in a situation where we have axis symmetry. So everything will be one-dimensional in analyzing these operators across a gluing region. What we have done here is a very easy case, time symmetric. We look at this Hamiltonian operator on the sphere, and we compute two things. We compute the element of the kernel. So I will really not elaborate this too much, but so you are in an axisymmetric situation. So we have an interval of this angle theta at infinity. So we solve something which is really only one-dimensional, where we do a gluing of Schwarzschild. It could be two Schwarzschild metric, or Schwarzschild and Minkowski, by choosing M1, M2 any way you want. So and we solve in the gluing region, which in that setup reduces just to an interval. So we have an interval in this variable theta with singularities at the boundary. Our operator is Fuchsian. It has a two-dimensional subset of bounded solutions. So, this kind of things. And so there are two things we plot. We plot the element of the kernel, and we plot, which has, it's something that is unrelated to the actual choice of the seed data. And then when we choose the seed data to be something that connect Schwarzschild to Minkowski, we plug the actual solution. And so this is given by, okay, so sorry, it's really a bit technical, but this is a final picture I can show you where, so this is a function that tells you across the gluing region how the shape of the kernel element is, and this is a picture for the solution on the sphere at infinity. So of course this is completely, there is no intuition you can pick up in these two pictures, but The last one is more interesting because here you connect 0 for Euclidean to something small here, maybe 1 for Schwarzschild. And so this is a picture of what the curvature coefficient, let me show you here. This is our definition. You take the Ricci curvature and you call chi over r cube, the effect of the curvature at infinity, right? So you have 0 on one side, you have 1. This is our choice for the mass of Schwarzschild in the other side. And you are on the sphere at infinity, everything is 1 over r, and you wonder how these two things are connected. And the answer is given by this picture, where you have 3 different coefficients that represent the curvature. And it's quite interesting that it's non-monotone, so you do connect 0 to 1, say, but you connect it in some non-monotone way, but that's the answer to the question of describing 1 over r terms. And maybe in just a few seconds, let me conclude by maybe saying that we have on one side, we have a fundamental construction method saying that there is a map and the map is introducing some element of these kernels. And then we can apply it and somehow play with the energy momentum modulators, which are kind of deviation from the ADM vectors. And by playing with parameterized family of seed data, I explained that a couple of times, applying implicit function theorem, you can get essentially anything you want. And it has also been applied as an initial data set in a result of global existence. And myself, following the work of Hans Lindblad and Igor Onionsky, I had introduced, I mean, this is really a long project with UMA, the possibility of evolving massive fields by this technique. So everything I described today can be taken as an initial data set for this theory. And this theory applies to metric perturbations, this evolution results, where the exponent is greater than 1/2. And otherwise, the whole lecture today I was able to cover any arbitrarily small PG. This geometric decay of the metric can be arbitrarily small, even the mass being ill-defined, because I show you at some point that the only thing that I care is the difference between the seed data and the solution, and the difference has enough decay to define the mass and discuss the mass like I did today. Thank you very much.